Hi, this is Professor Dorr. This is EE3 Tech 10, lecture number 26. This lecture is the first of two lectures where we're going to review our EE310 course. In this lecture, we're going to cover chapters 8, 9, 10, 11, and 13 of our textbook. And then in the next lecture, we're going to cover the remainder of the course. And then that will be it for the course. So in the beginning of the course, I mentioned that one of the big things that we were going to do as part of EE310 was I was going to take Ohm's law, which you all knew up here, and I was going to put it right down here. And what you've seen in EE310 and EE330, if you're taking that also, is that a lot of these courses are just Ohm's law. And you see a lot of KVL on the fly and KCL on the fly. And the purpose of that is really to take Ohm's law and put it in your heart where it belongs. So let's start off by looking at voltage and current sources. I like to look at voltage and current sources using just a current versus voltage curve, because it really just shows the essence of what they are. For example, let's look at this voltage source. This voltage source will put out 5 volts at any current you want. So it will supply whatever current it needs to put out 5 volts DC. So its IV curve is going to be 5 volts regardless of the current. It's just going to keep going right up here. So it's a voltage source. And of course, everything is a Thevenin source. That's Dorr's law. And this particular idealized EE310 voltage source has 0 Thevenin resistance. But I always like to think of sources as having resistance because in reality, everything does have some source impedance. You've seen that's especially important in EE330. So here's our voltage source. Puts out 5 volts at any current it has to, because there's going to be 5 volts right here. Now let's look at the traditional current source. For this current source, here, the current is going to be 3 amps. And it will put out whatever voltage it needs to, such that it puts out 3 amps. If I connect this current source to an egg, you're going to get 3 amps through that egg. Probably a reasonably high voltage because the resistance of the egg is pretty high. How about my eraser? Let's connect the current source to the eraser. You're going to get 3 amps through this eraser. You may get 1,000,000 volts, but this is a current source. It's an idealized current source, and it is going to put out those 3 amps. And just like every source is a Thevenin source, since Thevenin sources and Norton sources are the same, this is a Norton source. But its Norton resistance is going to be very high. Okay, so now let's look at some of the terminology that we introduced in EE310. We didn't always show every DC voltage source using a little round circle and a plus and minus. What we did is we just showed a little plus 5 volts, showing that this was connected to plus 5 volts. We do that because in schematics that you're going to see in industry, lots of things are going to go to 5 volts or 3.3 volts or 1.8 volts. And we don't want to draw wires between every one because it's going to make the schematic way too busy. So for common things like your power supplies, we'll just draw a little arrow and put 5 volts. And I wanted you to be thinking about that in EE through 10, so you'll do well in your interviews and get good, good internships and good jobs. So what this really means is 5 volts with respect to ground. And I also did things like I would label something like this, just VA or VB or V whatever. And the implication is that is with respect to ground. So just trying to get you a little more of an industrial feeling, and most of you picked that up really nicely. Let's do a couple of little Ohm's law problems here. We'll start off with this one on the left, and let me give you just a second to take a look at it. Okay, so what you see here is I want to know this voltage right here, and I've got a couple of resistors. This one goes to ground, and I've got a current source. And I intentionally didn't show you where this current source went. I just kind of drew a squiggly line and said, I don't really care. And that's perfectly fair, because this current source is going to do whatever it has to do to get that 2 amps through here. So I don't really care what is connected here. Of course, in industry, I'll absolutely care. But this is EE310, and I want to keep things idealized. So we've got 2 amps going through here. So let's see, that means I'm going to get 14 volts across this resistor. It means I'm going to get 6 volts across this resistor. Hey, wait a minute, one end of this resistor is ground. I've got 2 amps going through 3 ohms. So let's do KVL on the fly. Start at 0, go up 2 amps times 3 ohms. I get 6 volts right here. And I can also say 6 plus 2 times 7, or 6 go up 14 gives me 20 volts here. So just to pound in the idea of this current source, let's say that instead of a squiggly line, this is connected to my eraser and then ground. So this connects to the top of my eraser, and down here connects to the bottom of my eraser and to ground. So let's do KVL on the fly. Start at 0. Go down 2 amps times a mega ohm, and I get about -2 million volts right here, don't I? Because KVL on the fly, start at 0, because this end of the eraser is grounded, and it looks like a 1 mega ohm resistor. So from 0, I go down 2 amps times 1 mega ohm. I have -2 million volts right here, but I still have 6 volts right here. Okay, let's do another one. Here we have a 1 volt DC source, and I have my resistor here, and I've got a current source. Looks like here I showed it to ground, but I didn't have to. I could have connected it to my eraser to ground, or to Bella, because she's sitting right down there, but I wouldn't want to do that. So let's do KVL on the fly. I know I have 1 milliamp here, so plus to minus, I'm going to have 1 milliamp times 1 volt here. So that's going to give me 1 volt plus to minus. So here we go. Start at 0. Go up 1 volt, because of this 1 volt supply, and then plus to minus 1 volt, go down 1 volt. And this point right here is at 0 volts. So Ohm's law. Most of you got pretty good at this over the last few months, and I'm really glad about that. So in EE310, when we start off in chapter 8, which is our second order systems and transient response and steady state responses and such, we came up with what we call the rules. And I kind of like this little graphic because I divided it so that the left side is for one half of your brain. It's kind of that verbal side of your brain. And the right side of this graphic shows the equation that you'll use. And what I'll usually do with problems like this is I'll start on the verbal side. I'll start on that intuitive side until I see what's going on, and then I'll jump onto the mathematical side so that I can work it out. I love mathematics, but I trust my intuition more. The mathematics is a tool. So let's start off. For the inductor, let's say the inductor current cannot change instantaneously. Now, if you want to go over to the physics department, of course, they'll tell you, well, you can't move energy from one place to another in 0 time. That's fine. But for our purposes, let's say the inductor current can't change instantaneously. And the way we represent that with an equation is the inductor current at time 0 plus is equal to the inductor current at time 0 minus. Now, a similar rule holds for capacitors, and it comes from the same place, from the physics department, where they say that you can't move energy from one place to another instantaneously. And we're going to say that the capacitor voltage cannot change instantaneously. So mathematically, we'll say that VC of 0 plus is equal to VC of 0 minus. Now let's say some can rules, because these were some cannot rules. The inductor voltage, it can change instantaneously. So I can change the voltage across the inductor instantaneously, and I can change the current through a capacitor instantaneously. And you might ask, doesn't this violate the laws of physics? And I'm going to say that the energy in the inductor is 1/2 Li squared. So it's proportional to the current. And here we're talking about changing the voltage, where here we say the capacitor current can change instantaneously. Well, the energy stored in the capacitor is 1/2 CV squared. So we can't change V. Yep, there it is. But we can change the current. So here are the first 4 rules. Now we're going to say that at steady state, meaning di dt is 0 for an inductor, plus all the other derivatives, but we're going to worry about just di dt, or in other words, we're at steady state. Nothing is changing with respect to time. So at steady state, the inductor voltage is going to be 0. And we're going to say that mathematically by just saying the voltage across the inductor at infinity is equal to 0. And this, we can make a lot more sense out of this if we want. First of all, when we got into AC circuits, we learned that the impedance of the inductor is j omega L. And since at DC, omega is equal to 0, j omega L is going to be 0, so the inductor looks like a short circuit. Hello, VL of infinity is equal to 0. And of course, we can also say V sub L equals L di dt. And at steady state, d anything dt is going to be 0, so V sub L is 0. So this makes good sense, and we can show it multiple ways. Now for the capacitor at steady state, we're going to say that dV dt equals 0. So the capacitor in the, the current in the capacitor is equal to 0. I equals C dV dt for a capacitor. Where is it? Here we go. And since we're at steady state, d anything dt is 0. So of course I is going to be 0. Now let's go to our frequency domain interpretation. The impedance of the capacitor is 1 over j omega c. And so omega is equal to 0. So the impedance of the capacitor is infinite. So of course it's not going to have any current. So we can show this a lot of different ways. But when we first started off in chapter 8 and we were all struggling with this stuff, these rules came out to be really helpful. And I use especially these 4 rules all the time. And I always start off by triaging my circuit with the verbal side, and then I jump over to the math side and I work out all those details. Okay, so let's look at an example here. And I always like to triage everything, and let's see, I got a 5-volt source. Looks like at t equals 0, the switch closes. So that means before 0, I'm not going to have any current in here. Let's just kind of keep triaging. It's tempting to just say that, well, if the switch is open, then this thing's dead. And actually, most people in industry would say that. But let's kind of formalize that. So if this switch, first of all, at t equals 0, yes, the switch is open, but we're at steady state. So I know that there is no voltage across this inductor, right? Because we're at steady state. So the voltage here is 0 because it's ground. The voltage here is 0 because we have no voltage across the inductor at steady state. And I know I have no current. So I have no voltage across here because there's no current. So that means I'm 0 here. So yeah, there's nothing going on here, but we formalized that. Let's keep triaging. We're going to close the switch. When I close the switch, I know that I can't change this inductor current quickly. So the voltage, so the current is going to stay the same. So that means I'm going to have no current through this resistor at t equals 0 plus. But boy, I'm going to have 5 volts here because this is a voltage source, and we just talked about what voltage sources do. So at t equals 0 plus, I'm going to go close, and this is going to connect. So I have 5 volts here, but I have no current through the resistor because I have no current through the inductor. So that means I'm going to be 5 volts here, 5 volts, go down 0 current times 10 ohms. That's going to give me 5 volts here. So at t equals 0, it looks like I'm going to have 5 volts here. Well, one of our rules says that we can change the inductor voltage instantaneously. So that's exactly what's going to happen here. We're going to get 5 volts across this inductor at t equals 0 plus. And this is so much fun. Let's just keep triaging. So at t equals infinity, we're going to be at steady state again. Anything dt is equal to 0. So I know that I'm going to have no voltage across this inductor. So that means the voltage here is 0. The voltage here is going to be 0. And I know the voltage here is going to be 5 volts. So 5 volts minus 0 volts over 10 ohms is going to give me a ½ an amp through here. So I look at this thing and I'm pretty comfortable with this. So here we go. We can do this fairly quickly now. I at 0 minus, we triage that to 0 because the switch is open. I at 0 plus, we can't change the current in the inductor quickly, so I at 0 plus is going to be equal to 0. Or we could say for the inductor, I at 0 plus equals I at 0 minus, which is 0. I at infinity, remember we're 5 volts here, 5 volts here because the switch is closed, 0 volts here. So 5 volts divided by 10 ohms is 1/2 amp. VA at 0 minus, no voltage across that inductor at steady state. So therefore VA at 0 minus is going to be 0. And then we showed in our triage that at t equals 0 plus, we're going to have 5 volts here. We're going to have no current through here because we can't change this current quickly. It's going to give us 5 volts here. So VA at 0 plus is going to be 5 volts. And we get a warm and fuzzy because we know we can change the inductor voltage quickly. VA at infinity is going to be 0 because there's no voltage across that inductor at steady state. VB at 0 minus is going to be 0 because remember, 0 volts here, 0 volts here because no voltage across the inductor at steady state. So that means, and no current, so that means we're going to have 0 volts here. VB at 0 plus, well, of course, that's going to be 5 volts because we're closing that switch, and that's what that 5 volt source does. And then VB at infinity is also going to be 5 volts. Now let's do VC. So VC is the voltage across this resistor. Probably should have called it VR, shouldn't I? At t equals 0 minus, there's no current. So it's going to be 0. At t equals 0 plus, there's going to be no current because of our inductor, and we're going to call, and so therefore we have no current through this resistor. We'll say VC at 0 plus is going to be equal to 0. At infinity, we have 0 volts here because the inductor is at steady state again. We have 5 volts here. So 5, 0. So VC at infinity is going to be 5 volts. Okay, now we get into the fun part. di dt of 0 plus. Well, here's I. It's the current through the inductor. It's also the current through the resistor. But we know that we have nice equations for di dt through the inductor. And of course, it'll be the same through the resistor, right? So we know that V is equal to L di dt at 0 plus. So di dt at 0 plus is going to be VA of 0 plus divided by L. Or in other words, 5 volts divided by 2 henries, which is 2.5 volts per second. Now let's get dV, 2.5 amps per second. Now let's get dVC dt, and this VC is really bugging me. I should have wrote R there because it's the voltage across the resistor. And what I'm going to do is say, well, I know di dt through here. That's also di dt through here. So we multiply I by R, and we get VC. So dVC dt is going to be di dt, which I think is 2.5 amps per second, times 10 ohms is going to be 2.5 times 10, that's 25, right? 25 volts per second. Okay. So now we're going to move to a problem where instead of using switches here, we're using the unit step function. And you kind of built up some chops with that unit step function in chapter 8, because it was a nice little substitute for a switch. But you really got built up your chops with it in the Laplace transform chapter, where we use the unit step function to make little pulses and things like that. So we're given this circuit and we want to find a whole bunch of initial and final conditions. So let's just triage it. And what do I see? Over here on the left, I see u of negative t. So if it were u of t, this 4-volt source would turn on at time equals 0. But it's actually u of minus t. And so in reality, this source turns off at t equals 0. So at t equals 0 minus, it's going to be giving you 4 volts. And at t equals 0 plus and afterwards, it's going to give you 0 volts. What does a voltage source look like that gives you 0 volts? Just for fun, let's go back up here. 0 volts. That means you're going to get 0 volts no matter what the current is, right? So where here you have a vertical line at 5 volts for 0 volts from this source, you're going to have a line here. And that's what a short circuit does. You get 0 volts no matter what the current is through that short circuit. Okay, so here's kind of a picture of things. We have this source going from 4 volts down to 0, and this source we have going from a short circuit up to 20 volts. Hey, look what I did. I didn't like the looks of this Norton source here. So just like we've talked about in class, it's a big old hanging curveball when I see a Norton source like this. Visualize it as a Thevenin source and see if it makes the problem look easier. I did that here, and yeah, looked a lot easier, didn't it? So I drew it this way, and of course my 4 u of t turned into 4 times 5 is 20 u of t. So I like this picture because I'm kind of showing myself, first of all, the simplified circuit, but also what my sources are doing. So at t equals 0 minus, what's this thing going to look like? You think about it. Okay, t equals 0 minus, this looks like it's going to be 4 volts, right? This is going to be a short circuit. So I'm going to have 5 ohms in parallel with this capacitor. Here we go. T equals 0 minus, we have 4 volts. And then we have our 5 ohms right here. So if you want, and we did this a little bit at the beginning of class, we can say, oh, this capacitor is an open circuit. I know some of you like to put little X's here or dots and show that it's not there. What I'm hoping you've picked up in 310 is leave the capacitor there. You know that there's no current through it. Because I want you to get more comfortable working with industrial kind of schematics. But here, I pulled the capacitor out. So the voltage at this point is going to be, and which voltage is this? It's going to be this voltage V. It's just a voltage divider of 5 and 3. So 5 divided by 5 plus 3 is times 4 gives us 2.5 volts here. And the current that we're looking for, which is the current out of that in this left-hand path, is going to be 4 divided by the sum of these resistors, or 1/2 amp. And so now we can figure out a few things. We know that we have 2.5 volts right here. And this is a good reason for leaving the capacitor in, because V at 0 plus is going to be equal to V at 0 minus. Or in other words, we're not going to change this voltage at T equals 0 because the capacitor will keep the voltage the same. So also, I know that this current I at 0 plus is not going to change. Why is that? Because it goes through that inductor. And we can't change the current through that inductor quickly. Now let's change the circuit for T equals 0 plus. What are we going to do? We are going to say this turns off. So to turn off a voltage source, we short it. And this, this supply is going to turn on. So we're going to show it here. So I'm guessing we're going to have a 20 volt supply, and then we're going to have just these two going to ground. T equals 0 plus, we have our 20 volts over here on the right. And then you can see we shorted the source on the left. So we know that I0 is equal to I at 0 plus is equal to I at 0 minus is 0.5 amp. And V at 0 minus, 0 plus equals V at 0 minus, and that's going to be 2.5 volts. So the current in the 5 ohm resistor is going to be 20 minus the 2.5, right, our 2.5 divided by 5, we're going to get 3.5 amps going this way. So KCL on the fly says I got 0.5 amp coming this way because I can't change that current in the inductor quickly. And I have 2.5 amps, I'm sorry, let's see. I have, I'm sorry, 3.5 amps coming from this side with this equation, 0.5 amp coming from here. So I have 4 amps going into that capacitor at T equals 0 plus. And now let's get dVc dt. We know that I equals C dV dt. So dV dt is going to be I over C, which is 4 amps divided by 1/10 of a volt. I'm sorry, 1/10 of a farad is going to give us 40 volts per second. Now let's find di dt for the inductor. So let's just think about that. Let's see. So di dt, I know that this is a horizontal component, and what you've seen me do in class is if I have a component that's horizontal, for some reason it just works better for me to say, hey, what's the voltage on the left and what's the voltage on the right? Because that way I can just subtract them and I get the voltage across the component. It's kind of a silly little thing, but it just kind of helps me with the bookkeeping. So if I want di dt, I really want di dt for the inductor. And I know that V equals L di dt. So di dt is V over L. So the thing I really need here, I know the inductance, is I need the voltage across the inductor. So that's what I really need to dig in and get. So here we go. This side, we know we have 0.5 amp. So let's use KVL on the fly. 0 minus 3 times 0.5 is going to give us negative 1.5 volts here. And I know at T equals 0 plus, I have 2.5 volts here. So I'm going to be negative 1.5 plus 2.5. So negative 1.5 minus a negative 2.5, because look how the polarity convention is going to give me minus 4 volts. So yay, I've got what I needed. I've got that inductor voltage. So di dt is going to be minus 16 amps per second for this problem. Now let's go to t equals infinity. So at t equals infinity, I'm still in the 0 plus configuration, meaning that this voltage source is shorted to ground and this one is turned on. So let's get the voltage right here. So we know that there's no current in this capacitor, and we're going to leave it in because that's what we do since we've made it through EE310 this far. And I know that the voltage across here is 0. So in my mind, I can just see the voltage divider of 5 ohms and 3 ohms. So the voltage at this point is going to be 3 divided by 3.5 times 20 is 7.5 volts. And the current through the inductor is going to be 20 divided by 5 plus 3. Forget about this negative sign for now. The current going this way is going to be 20 divided by 5 plus 3 is 8. And look at the convention. Positive current goes that way. Put a negative sign there, negative 2.5 amps. Okay, I'm going to take a quick break and get a cup of coffee. Hopefully you guys do also, and I'll be back in just a second. Okay, cheers. Let's now talk about, let's review our basic op-amp configurations. And the way we approach op-amps in this class is as an ideal circuit element. And we kind of mentioned that most op-amp circuits that you'll see in industry, the ideal approximations will get you a long way to the answers that you need. Or in other words, you can, if you look at a schematic and you see an op-amp, you can usually, at a first order approximation, treat it as an ideal op-amp. You don't have to do all the analysis. But the equations that I'm going to show you here are going to show you how to do that initial analysis. And of course, the ideal op-amp is the op-amp that we're going to use in 310. Now, of course, if you buy my book, there's about 25 pages on op-amps where it begins with the material that we have here, and then it shows you the most important non-ideal aspects of op-amps that allow you to use them intelligently in your designs. So buy my book, bring it to me, let me sign it. I'll give you $5 because that's my commission, because I just want you to have that book. I want it to do good things for you. It's only $45. So let's look at our basic op-amp configurations. And what I want you to remember on the exam is this formula. But let's derive it because it's so easy. You don't even have to remember this formula. It's so easy to derive. But on the exam, I want you to remember the formula. I don't want you to derive it. So we're going to do KCL at this node because our basic assumptions for the op-amp are that there's no input current into the op-amp, and when the op-amp feedback loop is closed, or when the op-amp is working the way it's supposed to, meaning it's designed correctly, there will be no voltage across these terminals. You might ask, why no voltage across the terminals? Because the gain of the op-amp itself is really, really high. So say the gain is 1,000,000 on this op-amp. It's not quite that high, but it's a good number to use. It is up in the thousands. So if we had maybe 1 volt across, 1 volt at this output, there'd be a microvolt across here. So that's essentially 0. So our ideal op-amp approximations are that we have no input current to either terminal. That makes it easy to do KCL at the terminals. And we have very, very high gain for the op-amp itself. And we can basically derive everything we need from that. So let's do KCL at this node. Vn minus 0, remember there's no voltage difference here, so this is 0, so this is 0. Vn minus 0 divided by Z1, or in other words, this term, plus V out minus 0 divided by Z2 is equal to 0, because there's no current here. And from there, you just solve for V out over Vn, and it's minus Z2 over Z1. You notice that I didn't use R2 and R1 because these are impedances, and they could be anything. I could have a big clump of resistors and capacitors and inductors here if I wanted, and I could have a big clump of resistors, capacitors, transformers, and inductors here. I could have a whole bunch of linear elements. All I have to do is just figure out what's the impedance of this clump and what's the impedance of this clump, and then put it into this equation. So this is what I want you to do on the exam. You don't have to derive this. I want you to know this equation. But let's do the second configuration. By the way, this configuration is called the inverting configuration. In other words, this goes up, this goes down. It's like a teeter-totter with the fulcrum being right here. Current goes in here, it goes out here. So this voltage goes up, making that current go that way, and this voltage goes down, making that current come out this way. So I think of it like a teeter-totter. Mathematically, here's our negative sign. This is the inverting configuration. Now let's go to the non-inverting configuration. And we're going to use the exact same ideal properties of the op-amp, namely oodles of gain here, and that means no voltage across the terminals and no current into these terminals. So of course we know that this voltage here on the negative terminal is going to be equal to VI. So here we go. VO minus VI divided by Z2, that current going that way is going to be equal to this current going this way, equals VI over Z1. So it's just another little KCL equation. So we take these and we grind through the math, and we get V out over V in is 1 plus Z2 over Z1. Again, Z2 can be a clump. It can be a couple of things in parallel where you'll see in my notes, I'll call it ZP. And Z1 also could be a big clump of stuff. So let's say that we have this op-amp configuration here. Just look at it for a minute. What is it? Looks to me like this one. However, Z2 is 0 and Z1 is infinity. 1 plus 0 over infinity, I have a voltage gain of 1. Why is this useful? It's a voltage buffer. It has very high impedance going in and very low impedance coming out. I use these in my amplifiers quite a bit with emitter followers, if you're in 330, or just an op-amp like this. Now, before we leave op-amps, let's just get one conceptual thing straight. It bothers some students that I say, oh, the gain of the op-amp is a gazillion. But then we come up with these equations which come out to gains of 5 and 10, 20 or something like that. Here's the idea. The op-amp itself has a gain of a gazillion, But when we put feedback around it, we make the gain of the circuit equal to this equation. So important to keep that those concepts straight. Circuit gain, V out over V in. Op amp gain, oodles. Okay, let's move into phasors. So for phasors, we have three forms. We have the rectangular form, x plus jy. We have the polar form, which is some radius, and we show it as a shorthand of phi. And we can also put an exponential form of the radius times e to the j phi. But really, a phasor is a complex number. And we can go back and forth between what we call the time domain and the phasor domain. And here's our time domain expression. V of t, and I try to use a little v here because it's time varying, is equal to V max, or the peak, of the cosine of omega t plus phi. So I've really described this cosine wave. I've got the maximum of it. This is how high and how negative low it's going to go. And the cosine, and here's the frequency, and here's the phase angle. Now, when we're doing AC circuit analysis, we're often doing it at one frequency. And so when we go into the phasor domain, we use this shorthand where we say big V is equal to V max at an angle of phi. So I tossed the frequency, didn't I? So that's kind of important to remember in phasor problems. So Euler's identity is a very useful thing, and I pointed this out in, I believe, lecture 6 on complex numbers and exponentials. And even though that material was a bit complex, and it's not material that you really used in the class, that was the most important lecture of this class, because that's the lecture that gives you the introduction you need to EE 410 and your DSP courses, and for reading most textbooks and articles on on signal processing. So, but let's repeat it here. Euler's identity says that e to the j phi is equal to cosine phi plus j sine phi. Or we can say that the cosine phi is equal to e to the j phi plus e to the minus j phi divided by 2. And if phi is equal to omega t, or in other words, the phase angle is going up linearly, then we say that cosine of omega t is equal to e to the j omega t plus e to the minus j omega t divided by 2. And in that lecture, I drew these as counter-rotating vectors. So here's our j-axis, or our imaginary axis, and here's our real axis. And this vector here is e to the j omega t over 2. And this phase angle is increasing linearly, so it's whirling around this way. And here we have this one, which is whirling around the other way because of this negative sign here. So this one's going this way, this one's going this way. In class, I made all kinds of crazy motions with my arms trying to show this, but the idea is this is a cosine. This isn't a complex number. And what you see here is as these counter-rotate, the imaginary part cancels all the time. See that? This one's going that way, that one's going that way. This imaginary part cancel with this imaginary part. You get the cosine. because imaginary numbers are really just imaginary, even though I think it's a really dumb term. So we represent the signals this way because in phasor analysis, we just deal with one of these vectors, and now it becomes complex because we can always put the other one in when we want because it just follows along like a little dog. So as you get into 410 and as you get into signal processing and you see this e to the j omega t business, I don't want you to get complex number phobia. I want you to go back to that lecture. I frequently, when I give that lecture in 310, I announce it to my former students, and usually we get some who come in because they really want to brush up on it. But you'll always have that lecture. You can always send me an email. I'll always send you that lecture. If you come to my office as a senior and even a graduate student, I'll explain it again to you. All right. So now let's look at phasors and components. So let's say that the inductor current is equal to I max times the cosine of omega t plus phi. Boy, that's pretty general. It has some maximum value, I max, and then it's a cosine at some frequency and it has some phase angle. So let's go back to our basic physics of inductors, which is V equals L di dt. And let's see what our voltage across that inductor looks like. So here's the current. So let's just take the derivative of this with respect to time, that's the di dt, and we'll multiply it by L. Here's the L, here's our I max, and of course we're going to have to put this omega over here, and the derivative of the cosine is going to be minus the sine. So it looks like I got all this stuff for my derivative here, so let's work this around a little bit, and we're going to leave our omega and our L and our I max, and we're going to jiggle our sign around and our negative sign, SIGN, to give us cosine omega t plus phi plus 90. And so now we're going to say that it ends up as omega L I max at an angle of phi plus 90 using our phasor notation. 90 degrees is multiplication by J. So it ends up as J omega L times I, or V divided by I is J omega L. And we say, how cool is that? That's where we get our formula for the impedance of an inductor, don't we? We can do it with Laplace transforms too if we want, but we just did it with our phasor notation, which is really Laplace transforms, but we're just not there yet. I can do the same thing for a capacitor, where I'll calculate that the impedance of the capacitor is 1 over j omega c. And I like to remind you of this little piece, because we have done so many j omega L's and 1 over j omega C's as we're hanging on by our fingernails trying to get through EE 310, that we can forget where this comes from. But don't forget, because it's not complicated. It's really pretty simple. So this enabled us to do steady state analysis for circuits. And later in chapter 15, we let S equal j omega, and we found that Z sub L, the inductor impedance, equals SL, and ZC equals 1 over SC. And hey, these work for both transient and steady state conditions. But for right now, we're just reviewing the steady state part. And what we did in chapter 9 and 10 allowed us to write the transfer functions that we ended up using in Laplace analysis. Remember, as we moved on up toward chapter 14, we wrote lots of transfer functions, And then when we got to the Laplace chapter, we said, oh yeah, here's the transfer function on the Laplace roadmap, and we already know how to do that. So for frequency response, we didn't do any problems with this, but I really want you to understand this concept because it gives you an intuitive feel for what transfer functions really do and what the frequency response is. And it's the way that smart people figured out how to design really clever filters that, you know, they're flat in the pass band and then they go down really steeply down to almost nothing in the stop band. And they design them using this technique. So let's just go over it once. So we can get the frequency response from the pole zero plot. And what we do is we take our transfer function and we factor that rascal. So now we know where the zeros are and we know where the poles are. How would we do this for a complex transfer function? That's easy. We let MATLAB do it for us. So in this form, I'm showing my transfer function as a bunch of zero terms and a bunch of pole terms. So now what I'm going to do is I can plot Z1 and Z2 and P1 and P2 in the complex plane. Here they are. Here are the two zeros, and here are my two complex poles. And one of our little trapdoors in EE310 is that if things are real, they can be wherever they want. But if things are complex, they got to be in pairs. Got to be in pairs if they're complex. We're not going to hammer that in, but it's just a good thing to remember. So what I'm going to do is I'm going to say, okay, I can plot these. And the magnitude transfer function, the magnitude of the transfer function is really just going to be the magnitude of this term times the magnitude of this term divided by the magnitude of this term divided by the magnitude of this term. So let's just show that. Here's the magnitude of the first term, here's the magnitude of the second term, blah, 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 third and fourth term. So each term now is the distance between the pole or zero and S and J omega. So what we're doing is S is equal to J omega. And here's the J omega. So we can make S wherever we want it. And each term is just this difference, just this distance, just the vector distance. So what you can see here is we can slide S wherever we want, and we just look at the magnitude of all these terms, okay? And that gives us the magnitude of the frequency response. So what I'm going to throw at you is, give me the magnitude of the frequency response of this function at infinite frequency. Okay, let's do it. I'm going to take my S equals J omega, and omega is a gazillion. So my dot is going to move up to the ceiling. And when my dot is up by the ceiling, really, all these distances are about the same, right? Because compared to the distance from here to the ceiling, the little difference is here, nothing. So really, they're all going to cancel, and the magnitude of this frequency of this transfer function is going to be 1.0 or 0 dB. And I can see that graphically. Now, I love this technique and I use this technique all the time, but we're not going to cover this technique on the final. But it's just a really cool little thing. And when you look at the filter tables and you use the filter tables to make just beautiful filters with beautiful responses, The smart people who came up with that stuff did it by looking at the geometry. And that's why filter types, like we have an elliptic filter type, or we have the Butterworth, which is actually named by Butterworth, but Dr. Butterworth, I assume. But for the Butterworth, all the poles lie in a circle. For the elliptic filter, all the poles lie on an ellipse, and that's how they get their names. So pretty cool stuff. I really like it. Hopefully you do too. Okay, let's do another problem. So here we've got a source here, 4 times cosine omega t, and looks like we've got some linear components here. It'd be nice to have a little ground symbol right here, but it really is only asking for I, so we don't really need one. But we want to get I sub t at a bunch of different frequencies, 0, 1, 5, 10, and a gazillion. And so before we do this problem, this is a steady state problem, but let's make sure we're good between the transient and steady state. Let's say I started with everything turned off, okay? And I just turned this source on. Well, obviously I'm going to get no current through here immediately. So that means that the current here is going to be, the current here is obviously going to be 0 when I turn it on. So it's probably going to start down here, and the voltage at this capacitor is going to be 0 when I turn it on. So yeah, it probably looks something like this. And then it's going to take a little while for things to kind of stabilize, i.e. the transient condition, to steady state. So here's the transient portion. Here is the steady state. And this is what we're talking about. This is where we're going, this is this steady state analysis that we're doing in this chapter. All transients have died out. When we get to Laplace, you'll see that we can handle both the transient and the steady state. But for right now, what we're doing is saying that the whole transient has died out, and this thing's been doing its little wiggly dance here for a long, long time. Transient portion, steady state portion, bridging between chapter 8 and chapter 9. So we're going to do this. Okay, so here's our circuit. And now we're going to do something else. Before we solve this at 1, 5, and 10 radians per second, let's do 0 and infinity, because we can do that pretty easily. At omega equals 0, we know that we're at DC, aren't we? So let's just look at this thing at DC. At DC, cosine omega t, omega is 0, so I just got 4 volts, right? DC. And I got no current through the capacitor. And I got no voltage across the inductor. Look at this, I'm going right back to the rules of chapter 8. So KVL on the fly says 4 volts here, 4 volts here. 4 volts divided by 2 ohms gives us 2 amps for I. So remember, omega equals 0, that's DC. Now let's make omega equal to infinity. And I'm going to say, okay, at omega equals infinity, J omega L is going to be equal to infinity also. So this thing looks like an infinite impedance. So I'm going to get no current through it. So I at infinity is going to be 0. So that's what we're doing here. We're just saying we can get the current at omega equals 0 and infinity by inspection. And here it is. DC, 4 volts over 2 ohms, 2 amps. And High frequency, this is an open, this is a short. Open says no current for I. So let's make our little AC picture of it. So we were given 4 cosine omega t. Looks like omega is going to be changing. And so Z sub L is going to be J omega L. Z sub R is equal to R. And Z sub C is 1 over J omega C. So now let's combine these impedances, because what I really want to do to get this, this current is make it look like just one impedance over here to the right. So let's do that. Here's our voltage source. Hi there, Bella. You want out? You want to say hi to everybody? Okay. Bella's been sitting at my feet for this whole lecture, and she's just decided that she wants to be an internet sensation. You're an internet sensation, Bella. All right, down you go. Okay, we'll go out. She doesn't want to go out. She just wants the door open. All right, door's open, Bella. Okay, so we go from here, and first thing let's do is let's combine these two. And you see, I usually will call this like ZP for Z parallel. That's just a little thing that I do. Here I'm just showing it's ZR in parallel with ZC. And now I'm going to crunch it up again. And I'm going to say that what we really have is ZL plus ZR in parallel with ZC. Where'd she go? Well, she actually went out. Amazing. She'll be meowing at the door in a minute. So I'm moving toward what I want by just having a single impedance here. So I is equal to 4 over Z sub L plus Z sub R in parallel with ZC. And you notice I'm never in a hurry to put in numbers. So that's going to be 4 divided by J omega L plus R times 1 over J omega C divided by R plus J omega, 1 over J omega C. That's my ZP. You notice later in the course, I did my little N over D trick to avoid what I'm doing here. Look at all this stuff I'm doing. I'm going to multiply top and bottom by R plus 1 over J omega C, and here it is, all multiplied out. And you remember that I've told you that when I asked for transfer functions, I frequently just, yeah, I knew you'd be meowing. I knew you'd be meowing. I frequently ask you for the unreduced answer because I don't want you to make mathematical errors. But here, I'm going to kind of process this one a little because I want to do some stuff with it. So I multiply top and bottom by R plus 1 over J omega C. And then I kind of multiply things out so I can look at everything by itself. And then I am going to multiply top and bottom now by J omega C. And I look up here and I go, oh, cool, I got a J squared. That's a -1. And so I put that in there. And I get myself an expression for I. So what I'm going to do is check it. Okay, you want to go back there again? Okay. Lectures are so much more fun with Bella. So what I'm going to do is I'm going to check this expression. So I know the answer at 0, and I know the answer at infinity. What are we doing? Asymptotic analysis, right? So we know that our circuit told us what our current at omega equals 0 and omega equals infinity, remember? And at omega equals 0, we know we got 2 amps up above, but let's check our transfer function. Set omega equals 0, I have 4 divided by R minus 0 plus 0. 4 over R is 2 amps. Yay, we got it right. Now let's go omega equals infinity. and we have I equals 4 plus J infinity divided by R minus infinity squared. That's a lot of infinities. Plus infinity, and infinity divided by infinity squared is going to give us 0. Yeah, we got this. So our asymptotic analysis is kind of telling us that our transfer function looks really good. So now, let's just use our calculator to compute the rest of this. And so we just grind through with our calculators. I'm an old person and I've already paid my dues, so I just have a calculator to kind of understand your world a little bit. Of course, I do it all in MATLAB, but you should do it on your calculator as much as you can so that you're more efficient when you take these exams. Okay, so we have our silly book notation, which they'll show this as I of t equals I max cosine 10t, and here omega is equal to 10, implying that what is in those parentheses right here should be in radians, but then they put minus 83.6 degrees. And yeah, I call that silly, but it really does kind of make sense. But it's kind of silly because do you have degrees in the parentheses or radians? I suppose if we asked the book author, he'd say, well, I have an angle and I can show it any way I want. And by the way, this is in radians. So it's all good, but you just kind of have to be careful when you see that. Let's move on now to power. And we have instantaneous power, which is how we introduced power, as P of t, meaning it's instantaneous or a function of time. And it's equal to the voltage across a device multiplied by the current through the device at any time. And we quickly said, you know, for resistors, the power is going to be going up and down and up and down and up and down. And for reactive elements like capacitors and inductors, they're going to say, here, I'll take the energy. No, you take the energy. No, I'll take the energy. No, you take the energy. And they don't dissipate any power on the average. They just take energy and then toss it back. They have a big energy party. Remember the example we did at the car wash where we showed that the power company came out and put a big capacitor across their blower motor so that they wouldn't have that big energy party going on between the generating station and the car wash because they didn't want to lose power in their transmission lines every time that happened. So instantaneous power was not real useful to us. What we really want is average power. Average power relates to how hot things get, and it relates to how much you pay for power and how fast your battery discharges. So we really care about average power. So we moved quickly in that way. And we said P, and you notice there's no T here because it's not time varying, is equal to 1 over T. And notice that this is only appropriate for periodic waveforms. As you get into communication classes, you'll do all this statistically. But for now, it's only good for periodic waveforms. So we're going to basically integrate the instantaneous power as a function over time. So we're going to integrate that power over one period of the waveform and then divide it by t. And that's going to give us the average power. You remember we showed piece of t is going up and down, and then when we integrate it, we get that area, and then we divide it by t, and our area, we kind of forced it into a rectangle. If you don't remember that, you can go back into those lectures. But what we ended up with is power, average power, which is not time varying. And if the voltage and current are sinusoidal, which in EE310 they generally are, unless they're DC, we say that the power is equal to 1/2 times the maximum voltage times the maximum current times the cosine of the angle between the voltage and the current. Looks complicated, but if you go back to the lecture, you'll see there's about 3 little lines of math where we get this, and it's really pretty cool. So this is appropriate for any device, this formula. Let's apply it to a resistor. The power is equal to 1/2 times the voltage max times the I max. And do we like this formula? Yeah, because the voltage and the current are in phase. So we have cosine of 0 gives us 1. So it's just 1/2 voltage max times I max times 1. For the inductor and the capacitor, the power is equal to 0. The average power dissipated in the device, based on our formula, which we said is good for all devices, it's 0. Why? Because the voltage and the current are out of phase. Remember, the impedance is J omega L, or 1 over J omega C, and that J throws a 90 degrees between the voltage and the current. So what we saw was, hey, only resistors dissipate power. So if you want to know the power dissipation in a circuit in EE310, and the reason I put that caveat in is that actual inductors have a little bit of resistance, either in the wires that they use or in the core losses that model as a resistor. But in EE310, our inductors and capacitors dissipate no power. So if you want to find the power dissipated in a circuit or the power from the source, remember, only the resistors dissipate power. And also, the power from the source is always going to equal the power dissipated in the resistors. So we moved quickly to RMS power, which is root mean squared power. And we get into concepts here, and these concepts are important. And in the book, it says the effective value of a periodic current or voltage is the DC current that delivers the same average power to a resistor as the periodic current and voltage. This looks complicated, but I don't think the authors of the book could have said it better. I think this is just a wonderful definition, but let's break it down a little bit. So here are 2 circuits. And here is an AC current source going into a resistor. And here is a DC current source going into the same resistor R. And so what we want to do is we want to find, we're given this AC, this current source value. I want to find the DC, or the effective value, that puts the same average power into this resistor. So in this case, the instantaneous power is going up and down and up and down and up and down. Here, the instantaneous power, since this is DC, is just camped there. And so I want to be able to relate this AC signal to this DC signal. Or in other words, the effective value of a periodic current in this case is the DC current, this I effective, that delivers the same average power to the resistor as the periodic current or voltage. So bottom line is we start off with this AC current, and we're going to now we're going to get its RMS value as a DC value. And I'm going to feel this resistor right here, and it's going to be just as hot as this resistor. Average power is going to be the same. Same power. So here, my current is going up and negative and up and negative and up and negative. Here, my current is just DC. And what we found for sinusoidal signals is that the effective value is equal to 0.707 times the maximum value. So we have this source, and the RMS value of this source is equal to 0.707 times Imax. And we did problems where we came up with all kinds of crazy AC waveforms, and you had to go through and calculate this integral. So we had funny little triangle things and stuff like that, and you did this integral and you converted those into RMS values. So for a resistor, the power is 1/2 Vmax times Imax, or in other words, 1/2 of √2 VRMS, right, because that's Vmax, times √2, change this so it's IRMS, and we have VRMS times IRMS. So pretty cool. For a resistor, we can just say the average power is the RMS voltage times the RMS current, and that makes it a lot easier for us. Or we can always say Vmax is equal to √2 VRMS for sine waves, not for wacky waveforms. Wacky waveforms, you have to go figure it out. A cool thing is that our modern AC voltmeters in our lab, I say modern to me because in the old days they weren't, but the AC voltmeters in our lab are actual RMS meters. They do that integration for you. So you can put whatever kind of waveform you want in there, and provided it's within the bandwidth that that meter can handle, you're going to get the RMS value. It's pretty cool. So for power problems, sinusoidal power problems, what I'll do is I'll get the voltage or the current across or through the resistors. So I'll get the voltage across the resistors or the current through the resistors, and then I'm going to use power in those resistors is V squared RMS over R, or it is I squared RMS over R. I can also say power is equal to V max squared divided by 2R, and that's just that √2 between max and RMS popping its head up, or Imax squared over 2 times R. So this formula or this formula, just depends whether you use RMS or maximum. So we'll get the current, we'll basically find the power in the resistors by just getting the voltage across them or the current through them. So here we go. So I want to find the power dissipated in each component. And so our strategy is, first thing we'll do is let's just ignore the phase of the source. We have an 8 at -40. I don't care what the phase angle is. I care about all the relative phase angles between things because I need to get these currents. But I'm not going to do the whole problem with a 40-degree offset when I'm just looking for power. So we're going to ignore the phase of the source. I'm going to get I1 and I2. And then I'm going to say the power in the 1 ohm is going to be 1/2 Imax squared times R. And of course, when I find these phasor values, they're maximum values. And the power in the 2 ohm resistor is going to be 1/2 I2 max squared times R. And then I'm going to check and say that the power of the 1 ohm resistor plus the power in the 2 ohm resistor has to be the power coming from the source. And that's going to be 1/2 times the source voltage times I1 times the cosine of the angle between the source voltage and the source current. This is really important. Make sure you understand this. What I'm doing is I'm saying that the power in the resistors better add up to the power coming from the source. So we're going to do our whole mesh analysis. We're all really good at that now. So I1 is equal to 1.7 at an angle of 14.63, and I2 is 2.6 at an angle of 41.23 degrees. And remember, I blew off this minus 40. I said, this is 0 degrees, folks. I don't want to deal with that minus 40. So these are with respect to the voltage source, which is at 0 degrees. So the power in the 1 ohm resistor is 1/2 times I1 squared times 1 ohm, 1.45 watts. The power in the 2 ohm resistor is 1/2 times 2.26, or I2 squared, times 2 ohms, 5.11 watts. Now let's get the power from the source. 1/2 Vs max times I1 max times the phase angle between the voltage and the current. Well, that's going to be the phase of I1, which is 14.63, and I get 6.57 watts. So the voltage in the resistors adds up to 6.56 watts. The power in the resistors added up to 6.56 watts, and that was also the voltage from the source. So everybody's happy, especially the physicists. Okay, now let's go into transformers. So we have coupled coils with inductance and mutual inductance. That was one set of problems that we did. And in those, these are non-ideal transformer problems. We dealt with the inductance and the mutual inductance because the coupling was not always perfect coupling. We had dots, we had dependent sources. And what's the practical part of coupled coils with inductance and mutual inductance? Radio frequency people have to always pay attention to this because their transformers really cannot always be treated as ideal. Where I've really used this is in finding problems on PC boards. And I know I've kind of gone on and on about this, but there are a lot of people that think that coupling between inductors on PC boards is just kind of magic. And a good PC board designer has a lot of good rules of thumb where they can usually avoid or help the engineer avoid these kind of problems, but not always. And the engineer is ultimately responsible. And if you're that engineer who can diagnose those kinds of problems, and this is the material that will help you diagnose those problems, you're extremely valuable. And I want you to all be valuable so you make lots of money and get a lot of fun out of your career. However, most transformers that you see can be treated as ideal transformers. And so when you're using ideal transformers, we have voltage relationships, current relationships, and reflected impedance. So what I'm getting at here is for transformers, we have mutual inductance problems, and then we have ideal transformer problems. So let's review ideal transformers. So for an ideal transformer, it's shown with a turns ratio, 1 on one side and usually n on the other side. And then we show this big old iron bar going through here, and that's the symbol for an ideal transformer. Kind of indicates that the coefficient of coupling is 1 because there's a big old piece of iron between them. and the dots establish the polarity. Here I drew the dots on opposite sides. And let's look at the relationships for ideal transformers. The turns ratio is N2 divided by N1, or just N. And the voltage on the secondary is going to be N times V1. Now be careful on this one here, because of course the dot is on the other side. And so in this case, it'd be minus N times V1. So now let's do the current relationship for an ideal transformer, which is I1 is equal to N times I2, or I2 is equal to 1 over N times I1. So these are the equations that you need for the voltage and current. Now, reflected impedance, we can say that Zn from this side is 1 over N squared times Z2. And you notice I don't have dots in this picture because I don't need them. I just want to find the reflected impedance. That has nothing to do with the dots. So let's do a quick ideal transformer problem. I've got a circuit here with some transfer function, and then I'm going to put it through an ideal transformer. How does that affect the transfer function? And you all say that you just take the transfer function and multiply it by N2 over N1 or N. So it's just N times H of S. Let's do a mutual coupling problem. And here we have a mutual coupling between these coils. You notice you're not given the frequency, so you have to be given the mutual impedance. If you were given the frequency, we would have given you the value of the inductors and the value of the capacitor, and you would have to figure out what the impedances are. But here, we don't do that. We're just giving you the impedances, and here's the mutual impedance between these two. Now you remember, before we dive into this problem, what do the dots mean? And sometimes you guys do problems and you come up with your own rules on the dots because it worked for one problem or it worked for another problem or something. And I always slap you on the hand and say, don't do that. There's only one rule to remember for the dots. And here it is, and it's right in the book and it's in our lectures, is if the current enters the dot of one coil, the current enters this dot, the induced voltage at the other coil will be positive at the dot, period. Actually, it's a dot, so it's period. So that's the only thing, the only rule that you can use for the dots. So our strategy for this problem, before we say that, is this a practical problem? I say it's a very practical problem because this is the way you can hypothesize mutual coupling on a PC board. And if your hypothesis looks like it works on paper and it matches what the circuit does, you nailed it. And we did a really cool problem with that back in the lecture. But here's our strategy. We're going to redraw the circuit with dependent sources. Then we're going to use the dots of the transformer to establish the polarity of the dependent sources. Then we're going to blow off the dots. We're not going to worry about them. We're going to write the mesh equations, and then we're going to get these currents, because that's what we're asked to do. So we'll first redraw with dependent sources. And I like to draw the voltage source right between the inductor and the dot. So I always like to put it there. It just kind of, it just makes it easier for me to do. You don't have to do it, but it kind of allows me to approach all the problems kind of the same way. So that's what I do. And so the first thing I do is just put my sources, my little diamonds between the inductors and the dots like that. And the next thing I'm going to do is I'm going to just slap in the value of the voltage. I'm not going to put in the polarity. So here I say that it's going to be J3, which is the mutual impedance, times I2 minus I1, or in other words, the current in this inductor, because it's the current in this inductor that's causing the voltage here. And so what I'll tend to do is I could have made this I1 minus I2, right? Just means that the polarity here would be different. But I chose for the first one, the current entering the dot, because it's just something I do for consistency. And what you're going to see is that makes the dot, it gives me a positive next to the dot here. But you don't have to do that. All you need is the mutual inductance times the difference in the currents. And for here, the value of this source will be M times I1, which is just J3 times I1. So now I've got my values, I got to put in the sources. So for this one here, let's start here. I1 is what's going through this inductor. It enters the dot terminal, so it makes the dot terminal of this one more positive. So here's how I assign it. And here, for this one, this voltage comes from the difference between these two currents, and I2 makes the dot more positive. I'm sorry, I2 enters the dot, so it makes this dot more positive. So I have a plus to minus right here. So now I've got my dependent sources. I don't worry about the dots anymore, no more dots. And I start writing mesh equations. And so here's my equation for I1, or for this mesh. Here's for this mesh. You can see what I'm going to do is first I'm going to just go around and write the basic equation. Then I'm going to group my I1 terms. Then I'm going to group my I2 terms. And then I'm going to throw all that into a matrix and invert the matrix. Man, do I wish I had tools that could have done this when I was in college. This was really hard when I was in college. It's so cool now. When you guys are my age, there are going to be things that are going to be cool that you're going to see that old Professor Dorr didn't teach you. And then you'll understand how I feel when I see these things. But I end up with I1 and I2. And that's it for that problem. Now let's look at an ideal transformer problem. And the way, this is a problem we did in class, and I used 3 different strategies to solve it. And so we're going to go through those 3, and you're going to find the ones that you like better. Hopefully you'll do it enough times that you'll be like me and you'll be pretty ambivalent to which way you do it. Okay, so we got 240 volts over here. We've got a 4-to-1 transformer. Ooh, look, the dots are on the other side, so we're gonna have to pay attention to that. Okay, strategy 1. What let's do is let's take the load, let's take everything here, and what we want to find is V out, right? I want to find this output. So I'm going to reflect this whole load right here to the transformer input. And that's going to give me just another impedance here. Then I'm going to compute I1. Now I know I1, I'm going to use our ideal transformer relationship to get I2. And then I'm going to say V out is equal to just I2 times the capacitor impedance, or I2 times minus J24. So really what I'm going to do is I'm going to roll this stuff up this way. I'm going to get I1, and then I'm going to unroll it back here. So the load is 16 minus J24. That is going to reflect to 16 minus J24 divided by n squared, or 1 minus J 1.5. So now let's take this reflected stuff and put it right here. And here's what it looks like. This is the reflected secondary. So now I can get I1 pretty easily. It's just 240 volts divided by 1 minus J 1.5 plus 2, and it's 64 plus J 32 amps. So I got I1. Now let's unroll it going to the right. We'll convert I1 to I2 by using our the current reflection rule, and we're going to take into take those dots into account. You can see I apparently did it after I wrote this because I put my negative sign up here, and then I kind of had to put it here, and I get I2 is equal to 16 minus J8. So the output voltage is going to be I2 times ZC, or I2 times ZC, minus 16 minus J8 times negative J24 gives me 429.3 at this fun phase angle. Again, we reflected the load to the transformer input. We got the current I1. We used our current relationship to get I2, and then we multiplied I2 by this capacitor impedance to get VO. Let's do another strategy. Now what we're going to do is we're going to solve for the mesh currents I1 and I2, and then we're going to get V out is equal to plus I2 ZC. Negative signs are my nemesis. So now we're going to solve for I1 and I2. So let's make some equations. We're going to go around here. Minus Vn plus 2I1 plus, okay, V primary, good enough, equals 0. Just like the seagull. Good equation, probably has too many unknowns. Here, we're going to say minus V secondary plus 16I2 minus J24 times I2 equals 0. And I have two equations in 4 unknowns, V primary, V secondary, I1, and I2. But remember, we've got relationships that relate this stuff based on the transformer, and we're going to lower the number of unknowns with that because V primary is equal to minus Vs divided by N. So in other words, watch that dot, but the primary voltage is equal to the secondary voltage divided by N, and I1 is equal to N times I2. Now remember, no, we're good here. So I1 equals minus N times I. You stay asleep, I'm almost done with this lecture. And so now we can relate things in here. So we'll say that I1 in equation 1 is equal to minus NI2, so I've replaced that. And V primary in I1 is equal to V secondary divided by the turns ratio. And so that reduces over here. And now I have two equations in 2 unknowns. And I would go on about how wonderful that is since I'm an old person, but I just did that 5 minutes ago. So I'll hold off on that. And I'm going to solve my equations. And I get I2 and V secondary. And I'm going to take I2 and multiply it by the capacitor impedance, and I get the exact same result I got before. So here we kind of did it the fun way. We came up with I1 and I2. We got 2 equations and 4 unknowns, and then we used the transformer relationships to turn it into 2 equations and 2 unknowns, and of course we got the same answer. Now let's do our third strategy. Here what I'm going to do is I'm going to remove that cap, and I'm going to represent everything to the left of the capacitor as a Thevenin source. And then I'm going to, when it looks like a Thevenin source, I'm just going to have a single source right here, right, and the Thevenin impedance, and that's going to drive the capacitor. So once I have my Thevenin source, I'll load the circuit with the capacitor and just use voltage divider to get the voltage across that capacitor. So we need to turn this into a Thevenin source. And there's no current. I want to get the open circuit voltage, because remember, the open circuit voltage is the Thevenin voltage. So with this cut, I have no current here. So that means I'm going to have no current here because of the way the current reflects. So I can get my secondary voltage pretty easily. Here we go. Start at 240. KVL on the fly says 240 minus 2 ohms times no current gives me 240 here. 240 times 4 is going to be 960. And I'm going to watch those dots this time and notice and remember that there's actually a negative sign there. So my Thevenin voltage is minus 960 volts. Now I'm going to get Z Thevenin by shorting the voltage source and measuring the impedance looking into the Thevenin source. And so when I short that in that voltage source, here I go, that's shorted out. And what I need to do is reflect this impedance over to here. And so to do that, you have to be careful with which side you're looking in, because it might be 1 over n squared and it might be n squared. Just depends which you're looking. If I wanted the impedance looking in here, it'd be this impedance divided by n squared. But if I want this to get this, it's going to be this impedance times n squared. And that can get kind of confusing. What I usually do is say that if I got less turns on this side, or if I have less turns on the far side, it means I'm going to multiply that impedance by the turns ratio. But that's just the way I do it. So we go through and let's just add it up now. Z Thevenin is going to be 16, duh, that's easy, plus this reflected impedance, which is going to be 2 ohms times n squared, is going to be 48 ohms. So here's what my whole circuit looks like. Here is all this stuff in here to the left of my vertical line here, represented as a Thevenin source. And then here's my capacitor. And I'm just going to use the voltage divider to get this voltage across the capacitor. It's going to be minus J24 divided by minus J24 plus 48 times my negative 960, and I'm going to get the same answer as I did before, 429.33 at an angle of 116.5 degrees. Okay, so this was our first review lecture for EE310. In a way, it was kind of nice to be able to do this as a recorded lecture, because you could see that I kind of went beyond the normal 1 hour and 15 minutes we'd have for our class. But we covered chapters 8, 9, 10, 11, and 13. So I will see you in our next lecture. Hopefully I'll see you all in office hour so I can go through anything in this lecture in whatever detail you need. I want you to understand this stuff, and I will see you then.